The principal driver of heat and matter through ecosystems is the daily variation of solar radiation. This means that at any time you measure any quantity related to this, basically the substance of biophysical ecology, you will have to account for this strong daily variation. And how do you analyze that? Usually you'll begin with a time series, a plot of temperature, humidity, whatever, versus time. You will get from this what we call a squiggly line plot, some up and down variation with a period of 24 hours. Sometimes that will be just fine. You can calculate an average, a standard deviation, or any of the other typical statistical measures from a time series, just as you would from any other data set. But sometimes analyzing a time series in this way obscures important information, and being curious scientists, we should want to find such things. But how do we do that? In this video, and in the video to follow, I will present two alternative ways to deal with these squiggly line data. These approaches may not always be applicable, but where they are, they can be a very powerful tool for summarizing and communicating to others the importance of your data. As you watch the video to follow, I want you to keep three things in mind. First, what does a time series tell you? And what does a time series not tell you? Second, what properties of a physical environment might be important to take into account when energy and mass flow through that environment are driven by a strong daily variation? And finally, what's the difference between steady state and transient state models of energy and mass flow? Don't worry if you have no idea what I'm talking about right now. The question will become clear in the video. The real world is an unsteady place. Let me be clear what I mean by that. Throughout this course, we've been introducing you to equations that help you analyze the flows of matter and energy through living systems. Most of the equations that we presented so far have assumed so-called steady conditions. That is to say, we assume a flow of something, heat or mass, is driven by some potential energy difference between 2 points. The flow is impeded by some resistance to flow. Alternatively, we can say that the flow is facilitated by a conductance of some sort. The equations that describe those things are all variants on Ohm's law, where current is the ratio of voltage difference over resistance. More generally, flow of energy or mass can be expressed as a ratio of some potential energy difference impeded by some form of resistance. Such systems are known generically as DC systems, DC meaning direct current. When we talk about, say, an energy flow, we're drawing what's known as an electrical analogy. And this means we can treat heat flow with the same tools we use to treat electrical current. In a DC world, the driving forces for flow are more or less steady. But the real world is anything but steady. It's driven in cycles, and this means we need additional tools to analyze it. The most obvious cycle in nature is the daily variation in solar energy flux. As the day proceeds, the sun travels through the sky, pumping in energy, which is then drawn out overnight. Energy in this instance does not so much flow through a system, as it does in DC circuits, as it cycles into and out of the system. This is known as an AC system, AC meaning alternating current, again by analogy to the alternating current that is supplied through an electrical outlet. In AC systems, there's an additional component besides resistance that governs energy flows. Energy can be stored. In an electrical circuit, storage is represented by a capacitor. In, say, a system involving heat flow, the capacitor is embodied in a thermal capacity or a specific heat. Suppose we want to analyze such a system, let's say temperature in the soil. We want to know how heat flows into and out of the soil through the day and night. The usual procedure would be to log the temperature at some time interval for a certain period of time. Those data, when plotted, give you what we might call the squiggly line, that is to say, the repetitive daily variation of temperature. What then? The squiggly line tells us that things vary through the day, but so what? We already know that. It turns out that there are some simple and powerful tools that let you glean more meaning from that squiggly line, and they also provide a simpler way to present the data. One such tool is something called a phase plot. We're going to apply the phase plot to a data set involving a Welwitschia plant, like this one here. Let me put these measurements into some context. We think that the large, low leaves of Welwitschia substantially alter the thermal microclimate under the leaves. To test this idea, we used eye buttons to log soil temperature over an extended period of time. You're already familiar with the eye button and how it works and what it does. In this instance, we followed soil temperatures from the 13th of January 2017 to the 9th of February of the same year, and we logged temperatures at hourly intervals. We wanted to know how the sun was pumping heat into the soil and how the Welwitschia leaf may be altering that. So we laid out an array of 4 eye buttons. We logged temperatures at 2 sites, one under the leaf and one exposed to the open sun. We placed 2 eye buttons at each site, one 2 centimeters below the soil surface and one at 10 centimeters below the soil surface. In this way, we could see the driver of heat flow through the soil, namely the vertical gradient of temperature. Okay, let's have a look at the data. Just to remind ourselves of the experimental design, here's a cartoon of a Welwitschia with its leaves spreading over the ground. We logged temperatures at 2 depths, at -2 centimeters and at -10 centimeters, at 2 locations, in the open ground exposed to the sun and in the shaded soil under the leaf. Pay attention to the color coding we've applied here. The data for each location can be expressed as a time series. For these measurements, there are 4 of them, one for each eye button. One in the open ground at a depth of -2 centimeters, another also in the open ground at a depth of -10 centimeters, and the same locations under the leaf, one at a depth of -2 centimeters and another at a depth of -10 centimeters. Okay, here are the data, in open ground at shallow depth and at -10 centimeters, and under the leaf, again at depths of -2 centimeters and at -10 centimeters. Here we have our classic problem of the squiggly line. What meaning can we extract from them, and how hard is it to extract it? Some things are clear just by inspecting the data. First, daily variation of temperatures in the open ground are large compared to under the leaf. That makes sense. This ground is directly exposed to the sun. Another thing we can say is the temperatures at a depth of -10 centimeters vary less through the day than do temperatures at a shallow depth of -2 centimeters. This is the case at both locations. All of this makes perfect sense, but the question arises, so what? Didn't we know this already? This is the problem with the squiggly line. But can we get more information if we can express the data in a different way? There is a way, and it borrows from some techniques in electrical engineering for analyzing AC circuits. One of the simplest is called a phase plot, which also goes by the name of a Lissajous plot or a Bowditch plot. Let's start with a simple circuit consisting of a resistance that spans 2 potential energies, PE1 and PE2, both of which vary with time. Energy flow across the resistor varies with the varying potential energy. The phase plot consists of plotting one potential energy against the other, in this case potential energy 1 and potential energy 2. Note that we've eliminated the time dimension here. For this circuit, the phase plot will consist of a straight line, indicated in orange. I've put little arrows on here to indicate that the plot includes a representation of time. Sometimes the current flows one way, indicated by the upward arrows, and sometimes it flows the other. The slope of this line tells us an important property about this system, namely its gain, or amplification if you will. As I've plotted it here, the line falls along a line of equality, indicated by the yellow dashed line. This means that the amplitude of P1 is equal to the amplitude of P2. At all times, the 2 potential energies are equal. We say in this instance that the gain is 1. In some circumstances, the line may be rotated about its central point. The slope indicates the gain. In this graph, now PE2 is amplified with respect to PE1. Its gain is greater than 1. This is the phase plot for a circuit limited by resistance only. No matter what the gain, the phase plot is always a straight line. Okay, what about a circuit that has a storage capacity, that is, with resistance and capacitance? When there's a capacitance, the two potential energies do not vary in synchrony. Rather, there's a phase difference between them. In other words, the peak potential energy in PE1 is shifted with respect to the peak potential energy of PE2. The magnitude of the phase shift is dependent upon how capacious the capacitor is. When there's no capacity, the phase shift is 0, and the phase plot, again, is a straight line. When there is a storage capacity, there's a phase shift, and this gives you a very different looking phase plot. The phase shift can be at most 90 degrees. Now, the phase plot is no longer a straight line, but is now a circle. I've put little arrows in here to indicate that this is continually varying. The arrows could, in fact, go the other way, but we won't deal with that complication here. Thus, we can use a phase plot to answer a very important question. How does resistance to energy flow and capacity to store energy affect the energy flow through the system? When it's resistance that dominates the behavior, the phase plot is a straight line. There is no phase difference in a resistance-dominated circuit. If storage capacity dominates the circuit, the phase plot is a circle. If both resistance and capacitance affect the behavior of the circuit significantly, the result is an oval phase plot. The relative importance of capacitance and resistance is indicated by the eccentricity of the oval. Well, that's all very nice and theoretical. What about real data? Let's have a look. Rather than as a time series, the squiggly line, we can express the Welwitschia data as a phase plot between shallow temperature on the vertical axis and deep temperature on the horizontal axis. Remember that temperatures are forms of potential energy. The phase plot tells us something very useful and very quickly. So, for example, all points up and to the left of the line equality indicates heat flowing down. Below the line of equality, heat flows upward in the soil. Take a moment to convince yourself of this. Here's the Welwitschia cartoon again to help us keep things straight. Let's take the temperatures under the leaf first. Here are the data, which form a series of loops, one loop corresponding to one day. You can see that the data cluster around the line of equality. There is a slight slope to these data, indicating a gain greater than 1, but not by much. The eccentricity of the oval is also slight. This is a system dominated by resistance. Okay, here are the data for the open soil. You can immediately see the stark difference. The temperatures again inscribe a series of oval loops, each loop corresponding to one day, and they are inclined at a steeper slope. Here, thermal capacity is more significant than it is under the leaf. The gain is also larger, which comes from the strong driver of heat from the sun. So, the phase plot tells us at a glance some very important characteristics of the drivers of heat flux in soils and the effect of the large leaves of Welwitschia. Okay, that was pretty interesting. The Lissajous plot can be a quick and handy way to tease something out of your data that may not always be evident from time series. Whether you use it or not depends upon how you're exploring your data. The bottom line is that it is a useful tool, easy to apply, and you don't need to stop at a simple time series plot to say something interesting about your data. In the next video, we're going to look at a more complicated method for teasing out useful information from a time series. Don't worry when it's starting to look mathematically intimidating. We'll also show you some tools to make it easy. So, without further ado, let's turn to that.